Okay, so this is section 4.3 of your textbook, acids and bases. Okay, sulfuric acid is not a toy. Okay, just telling you. Okay, so let's talk a little bit about the properties of acids. Anybody out there know any properties of acids? Raise your hand now. Tell me. Donna. Sour, yes. H plus, yeah, proton. H plus is a proton. That's good to know. Anybody else? They turn litmus paper red, yeah. We don't use litmus paper anymore. I don't know why they keep on using that question. We actually have something called pH paper. But it'll turn pH paper red, universal indicator near the bottom. But yeah, remember that though, what Claire said, because at the end of the year, on the STAR exam, which we may or may not have, it depends if the governor signs a bill, they always ask that question. Yes?
On the pH scale, it's 0 to 7.
0 to 7. Oh, we got on the pH scale, it's 0 to 7. Wow, we should just skip these slides. You guys got it. So here, produces H plus. I think that's what Lauren said. Very key, though. There's really no such thing as H plus in water. H plus is floating around. It's not the case. It's actually H3O plus. It's the hydronium ion. The hydronium ion. There's a hydrogen ion attached to a water molecule. Okay, tastes sour. Yes, we got that one. Oh, corrodes metals. We didn't say that one. That's a good one. Corrodes metals. Good electrolytes. Does anyone know what that means? Oh, well, we'll get to it. Reacts with bases to form a salt and water. Sometimes. Completely, sometimes not completely. There we go. That was Adam. pH is less than 7. Turns blue litmus paper to red. I put it on there. I don't know what this is supposed to, how this is supposed to help. It's some kind of something. Whatever. Turns it red. Here. Turns it red. Okay? So these are all good things to know. These are always in these standardized tests. They'll ask a couple of these. I think every STAR test has had this on there. Okay? Okay. And so there's some common acids. Vinegar, lemon juice, which is citric acid. Vinegar is acetic acid in water. Vitamin C is ascorbic acid. Baking powder, that's a very weak acid.
What's the most acidic acid?
They're all pretty acidic. So once you get down to HCl and hydrogen bromide, HBr, hydrobromic acid, they're pretty acidic. There's something called perchloric acid that's awfully acidic, but I think they're all like, it's kind of hard to tell them apart. I think if you looked it up on Google or something, they give you one, but they're essentially, with acids, it's kind of a bottom end you kind of tank out. With bases, that's not the case. With organic bases, we can get more and more basic. And so we have a young lady from India about 5 years ago at UCLA, passed away. She had a fire. She was working with a compound called T-butylithium, which I used to work with. It's a very basic compound that reacts vigorously in air and just combusts. And she was using she'd never been trained on how to use it. She was a young grad student. She got burns all over her body and ended up dying from it. So, but that's a base that functionally has a pH. We talk about 0 to 14 in water. That has a pH of about 50. So it goes off the scale, so it hardly has any hydronium ions, and it's really basic. But we're not going to learn about that definition of acids and bases today, because that's a different definition. We're going to learn about ones that are in water. Okay? So let's talk about I'm assuming properties of bases, right? I think you guys probably know these, so I'll go through them. Generally produces OH minus ions in water. What's an OH minus called? Hydroxide, hydroxide, hydroxide. If the OH is hooked to a carbon, we'll call it a hydroxyl. But basically it produces OH ions in water. Notice it's generally produced. Tastes bitter and chalky like Tums. You know why Tums tastes chalky? Because that's what it's got in it, calcium carbonate. It's chalk. Just bind it a little different. Not quite as tough as chalk, but it's calcium carbonate. And they add another aluminum sulfate. They add a few different things. They are electrolytes as well. Notice they're not good electrolytes. Acids were good electrolytes. Feels soapy or slippery. That's how you know you're in trouble. Get sodium hydroxide on your hands. And they, again, notice they react with acids to form salts and water. It's known as a neutralization reaction. We'll talk about that in a bit. pH is greater than 7. Turns red litmus paper to blue. This makes sense. Basic blue, I get it. Basic blue. Blue. Turns it blue. Okay? So if you look at some of these guys here, some common things. So Drano and oven cleaner are actually the same chemical. It's the sodium hydroxide. Okay? I actually made some today in first period with sodium metal with my class. Baking soda is sodium carbonate. Sodium bicarbonate. So the bicarb is a little reactive. Okay? I don't know what that stuff is back there. Oh, it's ammonia. Yeah, ammonia is a weak base, NH3. Okay? Okay. Make sure you guys got those. So they're all kind of opposites of the acids. And you guys have learned a lot of this probably in middle school. Okay. So here's some common strong acids and bases. Okay, so strong acids, these are what I call the big three. Hydrochloric, nitric, and sulfuric. You should know the formulas for these and whatnot. Perchloric acid I'm not so concerned about. But perchloric acid is, again, a very strong acid as well. So what's the formula for anybody for hydrochloric acid? Nick? HCl. HCl. How about nitric acid, anybody? Ooh. Donna? HN3. HN3? No, it's actually HNO3. How about sulfuric acid? Naveen? Yep, H2SO4. I forgot perchloric, but I think it's HClO4. I think perchloric acid is H. Yeah, I would definitely know these three. You know them like the back of your hand. You're going to be using them a lot this year. Okay. There's another acid that's not quite as strong as these. It's called HF. Has anyone ever heard of HF? What's that called? Hydrofluoric acid. It's not as strong as the other acids on the pH scale. It's a strong acid though, but it eats through glass. That's kind of cool. You've got to use it in plastic containers, otherwise it eats through glass. Can't say that about the other ones. Okay? And then really strong bases we're always kind of stuck with in water. I gave you an example of something called T-butyl lithium, which is not in water. It's an organic base. But when we're in water, we're kind of stuck with these hydroxides. And so the two most common ones you need to know are sodium hydroxide and potassium hydroxide. It turns out that barium and calcium are also very basic. The problem is they don't really dissolve in water very well. So technically they're strong bases, but practically they really aren't because you can't get them into water. So really the two that you really need to come in to get to know are these two right here for water. Okay? Sodium and potassium hydroxide. Yes?
And why is it important that they're aqueous again?
Because right now in this chapter, what we're learning about are just things. They're kind of going over kind of a hodgepodge in 4.1, 2, 3, and 4. Like, what does this have to do with oxidation reduction? What does this have to do with those precipitation reactions? And what does any of them have to do with molarity? They're kind of just trying to focus on a few things that they think we're going to use the rest of the year that occur in water. Okay. The acids and bases, it turns out there's a whole other area of acids and bases. There's two other definitions besides this definition. This is the oldest definition. It's called I think I'll get to it, but it's in fact, when you flip your textbook to section 4.4 on the back side, there's a picture of a guy, Savante Arrhenius, and that's the person who came up with this definition. Okay, so let's talk about naming. A little bit of naming here. I got disconnected. So binary acid is an acid that contains only two elements, one of which must be hydrogen. The other one is an element that's more electronegative. So this is a problem for you guys because we haven't learned about electronegativity. I actually just taught it to my class today. I can show you an electronegativity chart really quick because it's up here. Or it was up here and I erased it. Never mind. No, let's find it. I'll pull that other one back up. So it says it's a hydrogen with something that's more electronegative. Okay, this is the electronegativity chart. It's basic measurement from 1 to 4 of an element's ability to want to attract electrons. Hydrogen is 2.1, so it's kind of right in the middle. Most of our metals aren't very electronegative. They want to give electrons away. That's why they're all cations. They all make pluses. But if you look in the upper, as I say, the northeast corner, there's some action. And so all the acids are like HF, HCl, HBr, HNO3, right? HS, H2SO4. So it's always a hydrogen, these binary ones. I guess actually I'm talking just about these ones, HF, HCl, HBr, HI. These are all more electronegative than hydrogen. This is what? Electronegativity is just, I'll just give it to you in a nutshell. Fluorine's like, give me electrons. I want them, you know? It's like my dog. Ball, 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 ball. Okay? And then over here, these guys are like, do you want my electron? These guys over here, way over here. See them? The blue ones? Take my electron, please. So that's why I have so much sodium chloride, right? Because there's sodium. Chlorine's like, hey. Okay? So, anyways, this is an electronegativity chart. We study this in chapter 6 of our regular chem book, talking about the periodic trends. The flip side is if the periodic table is a rectangle, basically electronegativity increases that way. Okay? And the tie-in to what I just was talking about was a binary acid is one in which a hydrogen binds with an electron that's more electronegative. Okay? So hydrofluoric acid, hydrochloric acid. Okay? And so again, here's how you name them. You add the word hydro and then the ic and the word acid on the end. Okay? Then there's oxyacids. These are acids that have hydrogen and then oxygen and then a third element that is usually a non-metal. So it's hydrogen, oxygen, and then one of these. Okay? Here's some examples. I was right. Perchloric acid, HClO4. I think this might be the answer to your question, Patrick. This might be the strongest acid. Nitrous acid is almost like nitric acid, but it's HNO2, not HNO3. Again, carbonic acid. Of all these, a little mistake there. Of all these, you don't need to know these as much. Just know what an oxyacid is, okay? What an oxyacid is. Carbonic acid is something you should become familiar with. We'll use it a lot in class. H2CO3. We'll use it a lot. Because basically this is what is thrown in your soda. Okay, this is carbonic acid is what's put into carbonated sodas to make carbonated water. Okay. You've got that? So again, knowing hydrochloric, I always say the big three: nitric, sulfuric, and hydrochloric. We're going to use those a lot this year, especially hydrochloric. We use all the time. Okay. I don't think we'll be using. We'll be working with this and none of this. Okay. So, the Arrhenius definition. So it turns out that there's 3 definitions to acids and bases. The first one that ever was discussed was a guy named Arrhenius, and it was kind of a basic understanding because of where chemistry was at the time. People did reactions in water. People, way back then didn't have like ether and chloroform and all these really cool organic solvents to do reactions in. They were seeing acid-base reactions in water, which could even be in real everyday world things, like dropping lemon juice into water. They would see acidity, so these are kind of practical things. And so the definition that arose was for an acid was substances in water that increase the concentration of hydrogen ions, H+. Okay? Turns out that this is a very limited definition of what an acid is. It's the most limited. Okay? It's the only one taught to you in middle school. The truth of it is most acid-based chemistry that's done today in the research world is of a different variety. We speak of it a lot differently. Okay? And a base is just the substances in water that increase the concentration of hydroxide ions, OH. So that means your acid must have an H in it someplace, and your base must have an OH. Well, we've discovered since the many years that Arrhenius has proposed this definition that there's many acids and bases that have neither one of these things, but they'll burn you, they'll hurt, and they'll actually transfer electrons and transfer all sorts of things. Okay? So this is where the pH scale comes from. As H plus goes up, the pH goes down. As OH goes up, the pH goes up. Okay? So notice I've tried to put these, color code these a little bit. Acid and H plus are red, base, OH blue. So basically the pH is turns out the pH is a very simple log measurement of the hydrogen ion concentration. That's all pH is. It's a log measurement. Base is the opposite of the H plus concentration. Okay? And there's what I said. Problem, many bases do not contain hydroxides, for instance. So this would be where in my other class, we teach this at the very end of the year, acids and bases, kind of April-ish, May. And then we'll go on and talk about the other definitions. If you read your textbook, it's very clear. It says this is just one definition. We're going to learn about other definitions later on in class. One is Bronsted-Lowry, and then the other one, which is the most inclusive one, is G and Lewis acids and bases. Okay? And so here's just something to talk about acid strength. And what I'm trying to do here is make a comparison between strong acids and weak acids. Okay? Between strong acids and weak acids. And so you might want to just quickly write this down. Strong acid transfers all of its protons to water. A weak acid transfers only a small fraction of its protons to water. Notice I keep on calling H plus a proton. Scientists or organic chemists like myself call it a proton because if you lose, your hydrogen loses its electron, that's all that's left. It has one proton and one, it's just a proton. There's no neutrons or anything. So hydrogen is just a proton. In fact, when we acidify something, organic chemists like myself, we don't say, oh, we acidified it. We say, oh, we protonated it. We use that terminology. Okay, we protonated it. Okay, this is an important concept that right here: completely ionized and partially ionized. This is exactly why this is a strong electrolyte and this is a weak electrolyte. We'll talk about that. You can write these down. We'll probably talk about these when we get to Bronsted-Lowry definitions. We'll talk more about those, but if you can write them down if you feel comfortable. I don't think anywhere in this chapter it mentions conjugate bases or conjugate acids or anything like that. But write it. I just didn't want to change the chart on this one, just for that. Okay. And so you can sort of see a line being drawn between what a strong acid is and a weak acid. Okay. I guess it stands to reason if you're giving all of your protons away, you're going to be stronger than if you're not giving them all away. Yeah. Nope, they have a weak conjugate base. Exactly, because the base is so weak, it doesn't want to come back and give up that. Okay, we'll talk more about that later on. We'll have,
they would have to counteract each other. So.
Yeah, well, see, the thing, that's why it's strong, because it totally, completely goes one direction. And I'm going to the next two slides, I think, will help you out. Okay, so everyone got this? Looks like it. Okay. So here's an ionization reaction for strong acids. So this is what would happen if I took hydrochloric acid and put it into water. I do this all the time for our classes. I do it, and it always is kind of got to be careful when you do it. The rule of thumb is never add a small amount of water to a lot of acid. Always add your acid to a lot of water. If you do, you get steam and looks like hydrogen gas or chlorine gas. It gets kind of hairy. You got to be careful. But anyways, when you add them, you get two things, H3O plus and Cl minus. Okay? And the H3O plus, if you see, was this hydrogen got transferred to the water, and it left behind the Cl minus. So the answer to your question, Patrick, is this is the conjugate base of HCl, and it's way weak. Notice the equilibrium. There is no equilibrium. This is one-way arrow. Notice it says 99.996% at equilibrium is H+. That means there's no HCl for all intents and purposes in the solution anymore. It's all either H+ and Cl- have separated out. H+ can exist by its own, but it can exist on water. As the, what was this called again? I said at the beginning. Anybody? The hydronium ion. Okay? Hydronium cation. So that's a strong reaction. The key part of this, people, of this reaction for strong acids is this arrow right there. It just shows it going that way. I mean, they call this an equilibrium, which implies that the arrow goes back this way. This isn't an equilibrium. Nothing's going back and forth here. This is, I'm going to the right, and that's it. Over. Done with. Okay? So that's for strong acids. Okay. Let's look at weak acids. Here's a weaker acid. This is a Coca-Cola, phosphoric acid. Coca-Cola. The base this time is water. Okay? And I actually have the conjugate acids and conjugate bases. Okay? Conjugate base. Here's the conjugate acid. Because this is this isn't Heather E. That's the person who did it. That's hydronium. Because hydronium is a stronger conjugate acid, you have this going back and forth. And so that's how you know you have a weak acid when you see this. So you see it's going back and forth. It's going back and forth. That's how you know. Okay? I'll give you guys a second to put those down. So that's the fundamental difference between strong and weak is strong is just goes all the way, weak goes like this, back and forth. So this acid here, conjugate acid, is relatively strong, and the conjugate base are relatively strong compared to these. The other thing that you'll notice, we'll get it right now, in this one, water is acting as a base in both of these. In HCl, it's acting as a base, and with phosphoric acid is acting as a base. Okay. Okay. You guys got that? Let's go to the next slide. So here's base strength really quick. All molecules accept a proton, fraction of molecules accept a proton, between the difference between those two. Again, completely ionized, partly ionized, strong and weak. So they sort of follow the same form as acid. Sort of the same idea. So you could almost maybe go back to the other table you made and kind of add strong acid and strong base and weak base to it, other than the all molecules except a proton part. So here's an example of a strong base reaction. And this would be if you took sodium hydroxide. Probably, I kind of whipped these off of the web today early. This would be plus water. Probably should be in there. Goes to Na plus aqueous plus OH aqueous. The aqueous means that there was water in there. So if you look at this, it's quite interesting. In the first one, you had HCl plus H2O. Before, I showed you HCl plus H2O. And I said H2O down here was the base. If you look at here, the base now is NaOH. And in this reaction, H2O is actually an acid. So what that means is that H2O can be an acid or a base depending on who it's around. There's a term for this. I want you to write this down. I'll write it down, then I'll answer your question. Amphoteric. Means it can be an acid or a base. And so water is H2O is a classic amphoteric molecule. Yes, Lauren?
How can sodium be aqueous if it reacts violently with water?
So what happens is the reaction that's occurring is water's here, and what's happening is you're making OH, okay? And you're actually making, when you're in another one, you're actually making something called, let me double check this. Yeah. So the OH is coming off, and you're also making hydrogen gas, and you have to balance it. I actually did this reaction this morning for first period. I took sodium metal, and I threw it in water. It's kind of exciting. And what happened was there was a lot of gas being involved, which is hydrogen. But essentially what you end up happening is the OH here basically goes forth and plucks basically a hydrogen off of the water molecule, okay? And so then you're left with, that makes water, but then you're left with an OH. And so essentially they can kind of rearrange, and eventually you can lose two hydrogens to get hydrogen gas. But really what it is it's kind of a dissociation reaction. It's kind of like dissolving salt in water, NaCl. They kind of come apart. It's just that this does it much more violently. It can make hydrogen gas at the same time. Okay? But nonetheless, these split apart. And the key here again, though, is that when you put sodium hydroxide in water, it is an ion. It's called something called an ionization reaction. The arrow only goes this way. So nothing goes back to form the NaOH solid, okay? There's no NaOH solid. Here's a weak base reaction. This is ammonia and water. So this is pretty much what you might do if you're, I think most of the ammonia cleaners you buy are ammonia in water. I don't think any of them are pure ammonia, because if they were, they'd knock you out cold. They're pretty smelly, pure ammonia. So they're in water. And so when you put ammonia in water, you have this reaction ongoing. But notice the double arrow. That means that ammonia is reacting with water to make ammonium and OH. We call that ammonium hydroxide. Okay? But the ammonium and hydroxide are now reacting and going back to ammonium and water. So you're setting up a equilibrium here. Okay? And again, why is equilibrium? It's a weak base. So as soon as you go here, base plus acid equals conjugate acid plus the conjugate base. But these are both fairly reactive, and they go back and forth. Okay? So because there's no strong base here, basically you get this equilibrium. This is the agent that's actually doing the cleaning, by the way. This is the agent that's doing the cleaning. If you take something like liquid Drano and pour it down, you don't have this equilibrium. You have just OH, higher concentration, and that is the one that will dissolve hair and dissolve clogs and stuff. Here, this is a much weaker cleaning agent, okay? Like the oven cleaner stuff you spray, it's also sodium hydroxide. Okay, so this is our last couple slides. What happens when you react a strong acid plus a strong base? So that's where you want to get, because that's where the cool stuff happens. So, of course, we're going to pick the two obvious ones, hydrochloric acid and sodium hydroxide. And again, it's kind of funny, right? You take this crazy strong acid that'll burn you and this crazy strong base that'll burn you, and you get done and you make salt water. Salt water. It's not very exciting. In fact, this has a name. It's called a neutralization reaction. Kind of makes sense because no one's afraid of salt water. You should be afraid of the other two. Okay? You guys will actually do this reaction several times this year. The only difference will be you'll have a pretty color and it'll turn pretty pink. You try to get it to like Sophia's color of her top. That's the color you'll be shooting for. Okay? Known as a neutralization reaction. Now, I just talked about strong acid and strong base. On page 83 and 84 of your textbook, they actually kind of go over weak acid, strong base, and strong acid, weak base reactions. They don't go over it in detail, especially none with the calculations. They just kind of cover it. So I want you to be sure to study that, okay? Page 83 and 84. Turns out we use this reaction up here in order to determine unknown concentrations of acids and bases. And that's what's called the titration, acid-base titrations. And then some of the homework you worked on today, there was the formulas and there's ways to solve these problems. I'm pretty good at solving these problems, but I do have a PowerPoint that I'll post on my website right after class when I get my act together. But I do actually have the PowerPoint, and I'll just show it to you really quickly. So you can put away your notes. You can stretch out a little bit. You've got about 10 minutes. Just want you to take 2-3 minutes and stretch out. If you need to come see me about something, you can do that right now. I don't know if I'm going to assign homework. I want you to get focused on understanding the problems that I assigned 47 or whatever it is, okay? So make sure you understand how to do these calculations. So yeah, your homework is to go over this PowerPoint tonight.
So if I missed the quiz, I got my score on the quiz is what I got on the test.
Yeah, so let's say you get 90% on the test. I'll go back and the quiz was 9 points. I'll put 0.9 times 9, and whatever that number is, I'll put into your quiz. Does that make sense? So what it essentially does, it means your test is worth, for this unit, is worth 45 plus 15. So your test is just worth more.
All right.
Okay?
That's good.
Yeah.